Hello, thanks for tuning in. In today's episode, we will explore one of Michigan's treasures, the Zilwaukee Bridge. Located near Saginaw, Michigan, every motorist traveling up north today on I-75 crosses this majestic bridge. For those who are not from Michigan, up north is a location, not just a direction of travel. But if we travel back to 1960, motorists could travel Interstate 75 from southern Florida all the way to Lake Superior at the northern tip of Michigan's Upper Peninsula without having to make any stops, with one exception. At the Saginaw River in mid-Michigan, there was a 4-lane drawbridge. And over the next decade, automobile traffic increased significantly, and shipping traffic on the river quadrupled. Together, these factors created significant traffic jams. An article in the Owasso Argus Press noted in 1968, quote, "The bridge even caused a 56-mile-long traffic jam," end quote. Several solutions were considered, including tunneling beneath the river or constructing a tall, traditional steel or concrete bridge that would allow ships to pass underneath. The first option was dropped, as it was deemed too costly. The next two options were considered, but bids were $81 and $86 million respectively, and the federal government thought that was too much money, as they were covering 90% of the cost of this project. Finally, the least expensive option was proposed: a high-level, post-tensioned, segmental concrete bridge. The new structure would consist of two separate bridges, one for northbound traffic and another for those traveling southbound. Construction began late 1979, with a projected cost of $77 million, and was slated to be completed in 1983, or about 4 years' time. Bridge technology. Post-tensioned, concrete segmental box girder bridges were a relatively new concept in bridge building. At the time, this was the first bridge of this type in the state of Michigan, and the largest ever proposed worldwide. These wooden blocks, or segments, can be used for a brief demonstration. Matching surfaces, alignment, tensioning pressure. And there you have the principle of a segmental beam. As you can see here, it also makes for an excellent bridge. The segmental bridge was to be built from individual concrete pieces, or segments, which are hollow and rectangular in shape. The segments are joined with post-tensioned steel cables to form the deck or superstructure of the bridge. The segments were precast in a factory constructed near the foot of the bridge. Each segment was slightly different than the next, and each had its own blueprint. They were constructed serially or in the order in which they were to be assembled, and each was match cast against its ultimate mate, allowing a perfect fit during construction. About 10,000 pounds of reinforcing steel was used inside each segment. Each measured 73.5 feet wide and either 8 or 12 feet long. They weighed between 120 and 160 American tons. The bridge would be 125 feet above Saginaw River to allow the passage of shipping traffic underneath, and creating a bridge deck that included 4 12-foot wide travel lanes in each direction. Segments were transported from the fabricating plant to the bridge by a long flatbed truck and trailer that had a combined weight of 102 tons. Loaded with a concrete segment, the unit can weigh up to 262 tons. The segments were erected by a massive piece of machinery called a launching girder, which is 940 feet long. It stands on its own steel legs and can roll across these legs when necessary to move to a new position as the construction proceeds. A track-mounted crane atop the launching girder picks up the segments from the truck and delivers them to the location where they are to be erected. The launching girder apparatus weighs 1,700 tons. Workers could assemble about 4 concrete segments per day. Just prior to assembly, a special epoxy resin was applied to the faces that were to be mated together. Some jokingly said the bridge was glued together, but the primary purpose of the epoxy was to create a seal that prevents the intrusion of water, thus stopping ice damage from occurring between the segments. It is important to note that the launching girder and the truck hauling concrete segments are not only extremely heavy, but are entirely supported by the not yet completed bridge. An important part of the construction process involves following exacting instructions provided in the launching girder handling manual, which spells out precisely where the launching girder is to be placed and the location of other heavy construction equipment and materials during the erection of each individual concrete segment. Erection of the segments began in 1981 at the north end of the northbound bridge and proceeded southward. By August of 1982, all 52 piers needed to support the bridge had been completed, with the remainder of the bridge scheduled to be completed the following year. Each of the 2 bridges has 8 expansion joints that allow the decks to expand and contract with changes in temperature. Erecting the spans of the bridge that contain expansion joints poses unusual challenges. During construction, it is imperative that segments containing expansion joints behave the same as ordinary segments. That is, the expansion joints must be made rigid and unable to move until construction is complete. This is accomplished by using temporary concrete compression blocks inside the joint, along with 30 steel tendons. The accident. The launching girder was standing on partially completed spans at piers 11, 10, and 9. What happened next was barely noticeable to the casual observer, but added 5 years and tens of millions of dollars to the cost of the project. On August 28, 1983, just after the truck and trailer had delivered a new concrete segment to the launching girder, the temporary compression blocks in the expansion joint in span 11 on the northbound bridge began to crush, and the 24 steel tendons began to stretch. This caused a 300-foot-long section of the bridge deck to sag 5 feet on one end and rise 3.5 feet at the other, like a teeter-totter. The tilting of the deck section caused considerable damage. The top of Pier 11 was forced about 8 inches out of plumb, damaging the pier footing. The movement ruined the bearings and pulled apart some of the already assembled concrete segments. No injuries were reported. What caused the accident? The primary reason is the expansion joint was required to have 30 steel tendons, but only had 24. And there was a discrepancy between the, quote, design criteria and the launching girder handling manual. The latter allowed heavier construction loads on the bridge. Michigan Department of Transportation's investigation concluded that had 30 tendons been used instead of 24, and the construction loads limited to those listed in the design criteria, the failure would not have occurred. Repairs. After the accident, engineers concluded that the structure was basically stable, and the majority of the bridge remained undamaged. However, 3 significant challenges lie ahead. Replacing the damaged bearings on top of Pier 11 North, finding a solution to the damaged footing under Pier 11 North, and tilting the bridge deck back into position. Bearings are made of stainless steel, Teflon, and neoprene. They carry the weight of the bridge deck and transfer that weight to the top of the concrete pier, while also allowing for slight movement of the bridge deck due to temperature or heavy loads. During construction, the bearings are placed atop the piers, then a concrete segment weighing a maximum of 160 tons is placed on the bearing. However, rather than lifting a single segment, repair will require the entire 6,600 tons pushing down on the bearing be lifted to allow the damaged part to be replaced. That is 41 times heavier than a single segment, and suspended 138 feet, or 42 meters, in the air. To make matters worse, crews cannot simply erect a structure from the ground to lift the bridge, because the soil is swampy and would not be able to support such a heavy load. Engineers decided to first repair the damaged footing below Pier 11, making a much larger footing that could not only support the pier, but will also allow the erection of a steel frame that can then be utilized to stabilize and eventually lift the bridge superstructure back into alignment. The original footings were constructed by pounding H-piles, which are large pieces of metal resembling an I-beam, driven approximately 80 feet down to bedrock. And they do that using a pile driver that's diesel powered. Also, most of the footing was below ground, and earth had to be excavated in order to build concrete forms before the concrete could be poured. However, these holes would quickly fill with water if some sort of measures were not taken, as the holes were below the level of the river. Caissons were constructed around each area to be excavated, to act like temporary dams. This kept the water out and allowed the concrete to be poured around the steel H-piles, thus creating a nice concrete pad that was supported by steel beams resting on bedrock. Driving piles creates vibrations because the process involves pounding the steel into the ground using a driver that weighs several tons. To make this repair, engineers instead decided to drill 6-foot diameter holes to bedrock so they could fill the holes with steel reinforced concrete and create underground columns. However, due to the unstable, swampy soil, removing the drills would cause the holes to cave in before the steel and concrete could be inserted. And also, they wanted to dig below grade to pour the new footing, and this would cause the hole to fill up with water. These were difficult challenges, solved with one brilliant idea. If they could freeze the earth all the way to bedrock, the frozen ground would act like a caisson and keep water out of the dig site. Plus, frozen soil would allow holes to remain after removal of the drill, giving crews the ability to install steel and pour the concrete. In early summer of 1983, approximately 200 holes were drilled for refrigeration pipes. The pipes were inserted all the way to bedrock in circular patterns around the intended location of each underground column. By mid-July, the ground was frozen enough to allow drilling of the 6-foot diameter holes. An 11-foot thick footing was poured on top of these columns. However, the portion around the old footing was not poured at this time, as they expected the old footing to rebound when the weight of the bridge was removed. Now they had a huge footing that rested atop 6 underground columns, each column 6 foot in diameter, reaching all the way to bedrock. Pier 11 North still rests on this footing today and can be seen with Google Earth. It is much stronger than the foundation for any of the other 51 bridge piers. Next step was to erect a temporary steel frame from the footing to the superstructure. The steel frame will be required to support over 13 million pounds that was pushing down on Pier 11 North. A series of enormous jacks were used to transfer the load from the pier onto the steel frame. Once this was complete, they poured the remainder of the new footing, tying it into the old one and the bottom of the column of Pier 11 North. Once this was complete, the bearings were replaced. A 1,100-ton concrete block was poured on the ground beneath the failed expansion joint. This block was attached with cables to hydraulic jacks mounted above. These hydraulic jacks were used to move the bridge deck back into alignment. The cost of the repair was $6.8 million. Final positioning was achieved on March 13th, 1984. Even though the bridge had been scheduled to be completed 1 year prior, it would still take 5 more years before the bridge was actually completed. The state and the original construction companies agreed to part ways, and the state began accepting bids in September of 1984 from new contractors. The new company resumed construction in the fall, and by the time they stopped due to winter conditions, a total of 643 of the 1,592 segments had been completed. Construction continued, mostly without incident, and the bridge was finally completed September 19th, 1988, 5 years behind schedule and $40 million over budget, which in today's dollars would be $88 million over budget. I hope you enjoyed this. Thanks for watching. Questions, comments, leave them below.